One of the repercussions of our microscopic view of thermodynamics is thermal expansion. So if we know that these molecules, when we heat them up, get faster, move faster, they bounce into each other more often, and they actually spread out. Well, because they keep bouncing into each other, they spread out. If we go out and zoom out to a macroscopic level, we look at bulk material, so a length of wire, for instance, we will see that we get two general equations that come out of this, and they both are very similar. But we'll see that this wire, so we have a copper wire that we heat up, the molecules in there bounce around more often, and they expand. So we get what's called the linear thermal expansion. It just says that how much this wire will lengthen, or how much this block of iron will increase. So we have or steel. Say we have a steel railroad track, and we ask how much does it lengthen if we put it out in a hot day? Well, we look at what's the temperature change. Well, since each of these molecules is causing a small little expansion, we have to look at the total initial length. So we look at our initial length, we multiply it by our temperature change, and we multiply it by our linear coefficient of thermal expansion, or linear thermal expansion coefficient. And that'll tell us how much we change our length. So our new length will be L naught plus delta L. There's a similar one for volumetric expansion. It just goes as the volume of the original volume times the temperature change times the volumetric thermal expansion. And that'll tell us how much our volume changes. And you can take a guess that these two kind of are related, since one is a one-dimensional case. This is the three-dimensional version. There's a cool example that comes into play here, and it's called the bimetallic strip. So if we take two different metals, they'll have two different linear expansion coefficients. So they may have the same length, they may have the same temperature change, but this alpha may be different. So if they're not glued together, one will expand slightly more than the other. Well, if we glue them together or somehow bind them together, then when we expand them, this guy has to be larger than this one. So what happens is they actually curl. So there's a really cool example of this that we use. You can actually see it in a lot of temperature gauges. I use a bimetallic strip. So next up, I'll show you a cool little video of just heating up one of these dual bimetallic strips. So the arc length over here is longer than the arc length there, which is how we keep them together, but still have different coefficient of expansions. So it's kind of an interesting way to make a thermostat.